Head of Department Electrical Engineering to the University of Moratuwa, Professor Devin, and my colleagues from the Smart Grid Research Laboratory. Today, I'm going to talk about how high renewable penetration systems and inertia response. Now, this is a budding topic these days, because of the government discussions on how renewable penetration, how we should achieve renewable penetration in the near future up to 70%. So more research as well as development is concentrated on this area. And if you talk about, I would like to take this an opportunity to talk about a little bit about the Sri Lankan installed capacity. Now we know that we have a thermal capacity of 825 megawatts. So we have three 300 megawatt generators at Aluthge, but obviously out of which approximately 25 megawatt is being used for auxiliary power. Then we have 900, so it adds up to 825 megawatts. And when we talk about the other thermal generation in the country, it adds up to approximately 971. Mahaveli complex is the largest hydro complex in the country. We have an installed capacity of 813 megawatts, and if I'm not mistaken, the Mahaveli complex as well as Laksapana complex are working at full load during these days. So we have the Samnala complex, which is a relevantly small complex, having the Samnala power station, which is 120 megawatts, and Kukulanga 70. So the total synchronous or the total installed capacity of the country is 3,273 megawatts. Now this is obviously conventional generation. Now when we are talking about smart grids, as well as when we're talking about high renewable penetration, the figures may seem correct, because we are dealing with the load, and the load might seem correct because the renewable power, the renewable energy reserves will be catering for the demand. But obviously there will be a power quality problem. So today we are going to discuss this problem. Now, the inertia, how it comes into play, we'll discuss it. But before that, we are going to little bit see what the current situation in the country is. Now, the government, the presiding government, is about, their philosophy is to develop the service sector rather than the industrial sector. Why is it important when it comes to the inertial response of the system? Now, when we talk about countries such as Germany, where there is high industries, there are not only synchronous generators in the system, but huge machine induction motors, which are coupled directly with the power system. So the inertial response will also affect the system from these loads as well. So any rotational mass, it doesn't matter whether it's a generator or a load, but if there is more rotational masses, that means we can improve the inertia of the system. Now, the inertia constant is defined by the total kinetic energy of the system divided by the generation apparent power. Now, in Sri Lanka, the problem is this inertia constant, the seconds. Currently, the inertia constant of the system is it's 3.9 seconds. And if we replace all the installed solar embedded generation with synchronous generators, we can improve this into 4.2 seconds. Now, there is a 1 second drop between 3.9 to there is a significant drop from 4.2 to 3 seconds. Now, the reason is that when we increase the renewable energy share to the system, we are actually replacing the conventional generators, which we can use for primary frequency control. Now, because of this improvement, or because of this rapid development in the renewable power sector, what happens is, as I said before, the conventional generators are being replaced with solar PV as well as other renewable reserves, such as wind power. Now, wind, you might say wind power, we can see the turbine spinning, so that will be directly coupled. No, those days the Hambantota wind farm, we know that it is coupled via a gear wheels. So therefore, the rotational, there is a magnetic coupling between the system and the turbines or the generator. But nowadays, what they do is they generate the voltage from variable frequency, and then they convert it into DC, and afterwards they reconvert it into AC. So therefore, there is no mechanical coupling with the system. So that also is similar to solar. And of course, when we increase the frequency, obviously what happens is we are going to when we increase the renewable share in the system, obviously what happens is we are going to lose the transient stability of the system. Now, this was done by this chart was captured, done by in a conference held by Mr. Lakshita Veerasinghe, who is the Deputy General Manager of Transmission and Generation Planning at CB. Now, from this chart, we can see that when we are moving towards 70% renewable target, but we have to increase the share of solar and wind up to 6,007 megawatts. So that's double. We have 3,000 something currently, but we have to double the wind and solar capacity. So that is the problem which we are going to face in the near future when we are going towards renewable power. Now, is the country or are the policies made for us to do such research, or do we need to do such research? Yeah, if I go to the energy policy, national energy policy currently which we are using, these sections say that we have to find solutions in the renewable sector, in the renewable power sector. So it might be solar penetration, it might be wind power penetration, whatever. We have to find solutions for the problems arising from those renewable energy reserves. So these are the points or the clauses where the energy policy addresses those. So, for example, 3.7.7 says that the energy storage situation needs to improve. Now, we know that intermittency is one of the most discussed topics among solar, because when a cloud comes, the solar drops from a peak to almost zero. Or that's not almost zero; it drops to zero. Right? If you if we consider a rooftop solar, a small cloud can make the generation of solar from peak to zero. So we need to address that. And of course, if the solar panel is very cool, and then there is clouds all over the place, and suddenly when the cloud goes away, the generated power will obviously increase 1.5% times the rated power of the solar panel. So these questions needs to be addressed. So we need to understand that the energy policy, of course, says that we have to establish energy storage systems, and it also discusses about the it also it also discusses about using vehicle batteries of hybrid vehicles as energy system storages, but that also is a concern because in the country the second-hand market uh, of vehicles is too high compared to other countries. So we have to understand and we have to make a discharging model and how to depreciate the asset in a very methodical manner, because if not, that might be a good research for undergraduates or postgraduates even, I don't know. But I would say that that also needs to be addressed. Now here, now going to the topic directly of my presentation, we know that there is the power balance. Right? The power generation should be equal to the power demand. When the demand increases and if the generation is the same, what happens is the frequency reduces. However, in a case where the generation increases and the load keeps as it is, what happens is the frequency increases. So the best match is between when the load and the generation is same. But what happens if a sudden generation loss occurs? A sudden, let's say, for example, let's say, what happens if the Moratuwa Aluthge power station contributing 275 megawatt is suddenly discharged from the system? How will it affect the frequency? Now, that is being discussed in the next few slides. Now, for the simulations, I used power system simulation for engineers. It's now in the engineering aspect, we can use PSSC for dynamic studies, but the word dynamic is not used amongst researchers because it's not an official word. You can use the word transient or primary frequency control, secondary frequency control, and tertiary frequency control rather than using the word dynamic. But civil engineers and other uh, engineering practitioners use the term dynamic. Where and the uh, manual generation control is also called the dynamic system. But as soon as the system feels or is affected by the fault, that starts the transient condition when the governor operation takes over after a few milliseconds. Now, simulations which I have done and which I will be showing right now have three places in the system. We have the Putlam station, which is called Aluthge power station. There's the Polonnawa grid substation, which is a high loaded grid substation. And then there's the Samana power station, which is 60 megawatt per. So there are two 60 megawatt generators. So I will be using these one load center and the two load generator centers to show you how frequency changes in various aspects and when of generation is there. So here what I have done, I have used power system simulation. It is a very easy software, convenient software if you want to do system studies uh, because of few reasons. One reason is that the country, the national control center is using so does the transmission and the generation planning branch. So that comes in handy because retreat from those would make your life easy. And also we can model various generator types. And then we new versions. can also accurately accurately model the solar as well as wind fluctuations and them as well. So this the software comes in handy, but you need to understand is this software is not recommended for initial response. So I have used aided design of ESCAT and by HVDC Labs at Manitoba to, to understand the transient response of the system. For the dynamic response, where the governor comes into action and the manual controlling happens, use PSSC, but lab or PSCAT. So I'll tell you how I used it. Now, this is the national system. Now, a very abstract manner. We have three 275 megawatt generators, and the load center is Kelowna. We did four simulations actually. One simulation we had solar penetrate megawatt to the 400 megawatt of load to the frequency when a 275 megawatt of generation is being rejected. This is shown in this figure, and as you can see on the left graph, we can see that there is a fluctuation of the frequency. This is due to the solar fluctuation. Hits 48.4. We have installed under frequency load shedding. It's almost all the place in Sri Lanka. Schemes occur, and then the frequency is restored from governor response action. Now we in a balanced system where thermal and hydro are balanced, so 50-50, thermal 50 and the hydro 50. This is the solid line shows the big response. For the similar load, reduce the thermal for hydromax. Now, for example, the country right now is we are running at a Laksapana complex is spinning, high water levels. So we are using a hydromax scenario. But the problem in a hydromax is that there is no governor response after a while. Most of the thermal power stations are working at base load. When I say most, not by number, but by capacity. Let's forget about the gas. Let's small IPP, but like a power station as well as AES, Kerala PTM, together with Moratuwa, they work at base load, or their group setting is not that flexible. So we can see that even though there is a high thermal maximum, the thermal maximum graph, even though there is thermal maximum, there are quite a few hydropower stations working intact. They take the responsibility of recovering the frequency, and they have a good frequency response rather than a hydromax frequency response. But out of all the three, when we discuss the scenario where there is no where there is no solar, you can have a steady frequency response, and it won't go up to 40.4. Now, this is what I am talking about. So this part, the green color, sorry, the dotted line, the dashed line is what I'm going to discuss, and we are going to discuss line as well, where VSG come into play. Virtual synchronous generator. Call it synthetic. Yeah, we call it virtual synchronous generator. We call it as virtual synchronous generator. There are names. Now you see, this is a frequency. As soon as a disturbance, this is the initial response. This we have absolutely no control. And this response time, the characteristic response can be modeled more accurately in another software, such as after coming into this point, the development or the frequency recovery can be modeled easily and more accurately in PSS. So don't confuse both the softwares, because I have used both softwares. So as soon as it hits the value of threshold value, under frequency load shedding occurs, and then it recovers. If there is virtual synchronous generator, now what's a virtual synchronous generator? A virtual synchronous generator is a generator which is not a synchronous generator, but using batteries, lithium ion cells, most particularly in Australia, they use they have a battery bank, they model it as a generator, and they inject AC power to the grid. So that's what is in the eyes of a system control engineer, it might be seen as a synchronous generator. If you go to that plant, it's not generated, it's just a which specific control methodology. These are the under frequency load shedding schemes that are integrated in the country. As you can see, when 275 megawatt is rejected from the system, it goes to up to 48, and that part of load is being taken out. In reality, what we do is we have wanted to take an arbitrary grid substitution. I'll take Panipitiya to Ratmalana. There is a one. Then there are transformers 36, 31. I can't remember the capacity, but let's say 31.5. There are 31.5 transformers. Then 9 feeders. Now these 9 feeders are being programmed. One feeder is programmed for the first load shedding here, the second one is second load shedding. There's a program for frequency load shedding. So when it detects one of these criteria, it shuts down that. That's what happens in the reality. In PSSC, what we do is 48.75. We approximately know what is the order of load that can be taken out of the system by load shedding criteria. That's what simulated in PSSC. Now, modeling PV in the PV, we have to understand is how I modeled it, because it's not accurate enough. We have taken an average solar curve over the country. The second, how it changes, how the solar power has been changing over the whole country has incorporated here, and also there is a in solar. What we do is we take it as unit power factor and zero inertia. That's how we model it. And one thing which I have not mentioned here is that, example, we have rooftop solar, right? Now, take the Ratmalana grid. Now, Ratmalana, there are 9 feeders. When KDU, where I work, is allocate. They have allocated a feeder or a couple of feeders to KDU. Now we have rooftop solar. We have there are rooftop solar in 3 buildings. Of the system, it not only rejects its generated load, but it also rejects it because the solar is being taken out as well. So that is not modeled in the system in the PSSA model. So we can improve that modeling, but since we are only taking the 132 and 220, it's very difficult. If you want to go to the 30 and below to model, a load flow analysis would not be easy, but when it comes to dynamic modeling, it might be better off. Now, the other thing which I did was, I incorporated a unit factor generator with zero inertia, which comes into play as soon as a contingency occurs. A virtuous synchronous generator. Now see what happens here. The same manner, the battery energy system storage, without the battery energy system storage. The recovery, final frequency response is better off when there is a battery energy system storage. But is there a load shedding? Yes, there is load shedding. What happens if a 60 megawatt generator goes on? This is where things get interesting. When a 60 megawatt generator is taken out of the system, the battery energy system storage required, and it won't go to under frequency load shedding. And in fact, rises at 49.8 hertz. But if there are no, if there is no storage, what happens is the frequency load shedding criteria, and it hits it, and only afterwards it recovers. We need to understand is we can build up a battery which does not have the power for a 275 megawatt generator, but is it profitable? Is it useless? That is a debate which we medium scale power stations, such as in this case, the battery energy system storage save the system from not having load shedding. Now, at the moment, human is required, but at the moment it might require. But as far when we go more high and high renewable penetration, these systems will be a must, as the transient response would be very high, less inertia constant of the system. Everything in a summary box like this. We know that, and without the battery, so the battery energy system storage was 50 megawatts. So without it, results. So I don't want to go to the depths of them. You can see that load shedding will be cancelled off when battery energy system storage and a medium scale power station is taken out of the system. Now, afterwards, what I did was we isolated a feed, and I wanted to see whether we can achieve a smooth transition from a battery energy system storage to cater the power for that particular feeder until load shedding is completed and the system is restored. This I choose the 7th feeder of the Ratnalana grid substation. Now Here you can see the red circle is the Ratmalana grid, and the gray circle is a primary sub. So we have 33 kV feeders going up, and then we have the primary substation. Now, modeled all the subs, all the subs, all the loads, and since we are talking we can wait. They have a battery energy system storage incorporated at the 11 kV bus. So I want to tell you this. Now we are moving towards transient. So therefore, I from pieces I managed to get good result. So first, we had a small ESI model. This is the model which I developed. It's a very basic. This is textbook, nothing fancy. And the inductance and the capacitance were chosen, but faced problems. Obviously, there were harmonics, and as you can see, the 11 kV system, and there was no smooth transition, and the low voltage side also had not got transition. So 50 hertz. Now the system was 50 hertz. A problem occurs. The frequency drops, and once it goes up 49.5, which is the permissible steady state value, this feeder trips, battery and system storage takes over. Obviously, there. So, what is the remedy? Incorporating a VSG or a virtual synchronous generator, synthetic. This paper done in Japan, they have incorporated virtual synchronous generators. In Japan, there are two islands. You might know this. One island is 60 hertz, one island is 50 hertz. So, operating frequency, they are tied. We can't use lines. We have to use HVDC lines. They use HVDC lines. So they use HVDC lines to connect these two islands, and the power is flown from one end to the other. And to model this system on one island, they had VSG. So there are 4 VSGs, out of which I use the swing equation based VSG. The reason for this is that it's simple and doesn't need a frequency derivative, because if we need a frequency derivative, that becomes a problem because we are talking about the transient domain, and it needs to have a very fast action. So it doesn't need one. So yeah, it's easy to implement, and the PLL or the phase lock loop is used for synchronization purposes only. This is basic swing equation VSG model. This we all know, and the swing equation model I use, and frequency. This is the reference frequency. When into the reference frequency of the VSI, voltage source inverter. So the voltage source inverter frequency is determined by the VSG, and the amplitude is determined manually. Then when I didn't have a promising result, so when I wanted to see the PSCAD, how they do the frequency, how they calculate the frequency, I found out that they are calculating the frequency as follows. Now they have the three voltage wave, and they take the zero crossings for 6 and they get the average. So that's how they get the frequency. Now in a high harmonic uh, voltage waveform, this might not be the case. It might give us a nuisance answer. So this is the frequency which I got when I use the VSG, the virtual synchronous generator, with the VSI inverter. I enlarged it. You can see that it hits a threshold value and then it drops. So it hits a threshold value and it drops. The reason for of the frequency. So if the frequency has a slip, it goes. If you take the vector notation, there's a slip, and that's the reason for that to happen. So I wanted to see how people measure the frequency, out of which discrete Fourier transformation was one of the most popular. So I used it to understand the frequency response of the system. And the equation, we are familiar with this. And we got a straight line, nothing line of the fundamental frequency. This was also good. It was being good. Then what I did was, okay, let's do fast Fourier transformation. We got the fast Fourier transformation and we took the harmonics. So what is the order of, what is the amplitude? What is the order of harmonics in the fundamental? Sorry, what is the order in the fundamental? What are the harmonic orders? So this is what we got. So the blue line states 50 hertz. It's a dominant. It's the dominant pattern. Now after this point, the grid is the system, battery storage takes over, and after this period, battery and system storage is taken out of the system and grid is again. It happened. Now these things got interesting. When you talk, this was for a particular phase, say A phase. When I took the three phases, this was the fundamental frequency amplitude. It changed. This was due to the these were the and this was a nuisance. So what we did was we reduced the filter inductances. When we reduced the filter inductances, this was due to when compared to the lines. When compared to lines, the filter inductance was very large. So what we did was we reduced it. So when we reduced it, we got a considerable good frequency response. So this is the frequency response by using only zero crossing, which is apparently good. Now since now we are using PSCAD. Now initially we used PSSC. Now we are using PSCAD. And the same thing happened here as well. There was a slip and there was a frequency change. When I got the voltage response of the amplitudes, it was not but better, but there were small fluctuations. Amplitude of all the three phases, and you can see that there is previously you saw the three phases significant, but here you can see that when I enlarge it, it's quite promising. The frequency response was as follows of that system. So I was, and then the next part was to reduce this problem, the slip. So before moving on to that, what we did was we modeled the lithium ion battery. This is the lithium ion battery which I modeled, simple one. These are the authors. They have developed the model, so I used the same model in PSCAD. The typical lithium energy system storage and the model was as follows. And here we came to the finale where I installed, or not installed, simulated the battery energy system storage controller, which I developed to the 11 kV using batteries as well. Gave the power set and the Q set, or the reactive power demand, and the was, and we determine frequency and the voltage. So the frequency was determined by T, voltage was determined by the indirect current control method. But it had a following problem. No. Now we used this in PSCAD, but PSCAD there was a limitation. The limitation is we didn't have to go, we couldn't go up after 2500 Hertz in the switching frequency. Not 2000, even less. I was using 4.5. Now I think we can go up to more than that. But then I switched into MATLAB, where it was convenient for me to simulate it correctly. Now here we can see that there is now up to 4.9 seconds, the system, the whole Sri Lanka national system is coupled to this feed. And after 4.9 seconds, national system is taken out of the system. So this is where it happens. And you can see that it has an overshoot and reduces, has an overshoot, reduces, has an overshoot, reduces. And afterwards, it's okay. You take the transition, it's something like this. If you take the PLL response, obviously there is the initial frequency, and then after 4.9 seconds, it has a fluctuation, and there is another frequency fluctuation. We needed to stop this. We need to have a smooth transition. Problem was this. We had an upper saturation limit and a lower saturation, 50.5 or 9.5. So this was the problem. Had to change. So we changed by not making the frequency, but setting up the power deficit by adding the acceleration power to the system. Actually, the results were promising. We got a good result. There were here also at 4.9, there's a transition from system to the battery system. Obviously, there is no, you can hardly see any transitions. Frequency response was promising as well. Then we said, okay, we'll forget about the VST. We'll have just the VSI, indirect current control method, and let's see what happens. So as you can see, the frequency collapses after 4.9. Now we know that installing 11 kV would be a problem because we have to have capacitor banks, we have to have inductors and whatnot. But these places have already installed VAR compensators, capacitor banks. Can we use these for the mentioned method? Yes, we simulated them on the 33 kV feeder, where we used a 20 kV, 20 MVA or megawatt capacitor band as the filter, and we got a good result. Transition hardly noticed. So we managed to get a promising results, and now we are going towards the cost analysis on how to determine the capacity of the battery system storage for 11 days. But having these kinds of things around the country will ensure the system stability when it comes to high renewable penetration. Mega lithium ion battery bank is installed at Australia, 129, because they had a recent blackout, and Tesla managed to install it, and they installed it, and the blackout problem went away. South Africa, there is this island called Robben Island. Actually, there is a microgrid, and the frequency control is done by battery energy system storage. So, if you are talking about microgrids, if you are talking about smart grids, but we need these are Dornish Power System, Imperial Irrigation District at California. These are practical examples of where battery system storages are used for primary and secondary frequency control. Today, I managed to discuss about combining the ESG model and the indirect current control model by using PSCAD and PSSC as well as MATLAB to achieve a fluent or a unnoticeable transition between the power system and the battery system storage. And another factor which I have explained is the supercapacitors. Supercapacitors currently there is 2 megawatt within 2 seconds they can discharge. Supercapacitors are also coming into play because we know we have to understand this. Large machines are being replaced with renewable energy reserves. What happens? A large inertia is taken out of the system and be replaced by zero inertia. And therefore, VSGs also take time to respond because it comes with a close feedback, not like a Dodge generator. This is where debate begins. We call that power electronics are fast, but it's like say you're in a system where there is large when the fault occurs, the initial response is within the system itself. But what happens in VSGs and fast active power injectors such as supercapacitors is it has a natural delay. So we have to address it as to approximately 30 milliseconds. That would do. So within 30 milliseconds, we need to make sure that these inject power. So let's move forward. As engineers, we have to understand the emerging technology and face the challenges. There are debates. There are pros and cons of moving towards renewable energy. Obviously, we have to move towards renewables. There is no debate about that. But we have to make sure that our system is ready and steady for the renewable penetration. So once we do done, I think we will be better off. So LNG is currently being used as a transition fuel, moving towards renewable penetration. So those are good things. But what we need to do is to, as researchers, we need to make sure that smart technologies and without Sri Lanka is being controlled by a central hub, national system control center. See, so when smart grid topologies come into play, we take we localize ourselves and we have small microgrids, and we try to stabilize those grids. So I believe that we can do that, and spawning researchers. So I'll take the questions now. Thank you.